welcome to the deep dive. This time, we're really getting into a fascinating paper, kNN-SVC, robust zero-shot singing voice conversion with additive synthesis and concatenation smoothness optimization.
Yeah, this one caught my eye too.
For those of you tracking audio AI, this paper tackles a core challenge in zero-shot SVC, just making it sound, well, robust and good.
Right, consistency is key.
And the main breakthroughs here, okay, first they're adding back harmonic detail. WavLM, often kind of misses that richness for singing voices.
Which can make things sound a bit dull.
Exactly. So they use this clever additive synthesis method, think like richer, more natural vocals. Second, they've come up with some smart ways to smooth out the transitions between the audio bits they stitch together.
Tackling those artifacts.
Yeah, getting rid of those glitches, especially on longer notes. So the upshot is a pretty big step forward for creating natural-sounding singing voice conversions without needing, specific training data for every singer pair. Okay, let's actually get into the nuts and bolts of this.
Absolutely. And for anyone working in voice conversion, especially zero-shot, robustness is, well, it's the big goal, isn't it? You want to take any source voice, convert it to a target style you haven't seen before, and have it sound convincing.
Not like some weird robot imitation.
Precisely. And this paper hits right at the limitations of how we currently do that.
Yeah, as the paper lays out, the fundamental difficulty is pulling apart the content, the lyrics, the melody, basically what's being sung from the style, that unique sound of the singer's voice.
It's a classic disentanglement problem.
Right, and lots of methods kind of struggle there. You get weird results like the original speaker's voice bleeding through or the words sound mushy. It just tanks the whole conversion.
And what's really interesting here is that instead of trying to perfectly separate those things, which is super complex.
Yeah, notoriously hard.
They build on a framework that sort of sidesteps the issue. K-nearest neighbor voice conversion, or kNN-VC. It's a non-parametric approach.
Okay, non-parametric meaning.
Think of it like this. You have a massive library of sound snippets from the target singer. When the source singer sings a note or a phrase, kNN-VC dives into that library, finds the closest sounding snippets from the target, and then stitches them together.
Right, okay, so kNN-VC uses these self-supervised learning representations. In this paper, it's WavLM embeddings for every little chunk of the input sound.
Like frame by frame.
Frame by frame, yeah. It finds the nearest matches in the reference speaker's pool of WavLM embeddings, averages those matches, and then uses a vocoder, which turns those features back into audible sound to generate the final voice.
And it's generally known for being pretty good at keeping the speaker's timbre, the voice identity, and making sure you can still understand the words.
High intelligibility, good similarity, sounds great for speech.
Exactly. Works surprisingly well for speech. But when you try to apply it directly to singing, the paper points out two big areas where it kind of falls down. First is just how the singing voice itself is represented. Singing timbre, its quality, is really heavily tied to the fundamental frequency F0, the main pitch and all its harmonics, right? The overtones.
The stuff that gives it richness and character.
Precisely. And this is where WavLM, even though it's powerful for speech features, it doesn't quite capture all that harmonic detail needed for really convincing singing.
Okay, so WavLM probably because of how it was trained, maybe more on speech data.
Likely, yeah.
It doesn't fully encode those crucial harmonic bits that define a singing voice's texture. And the paper says this can make the converted singing sound kind of flat, dull even.
Dull, yeah. Or sometimes you even get these weird ringing sounds, artifacts.
Yeah.
Figure 5 in the paper actually shows this pretty clearly if you look at the spectrograms, the with and without additive synthesis pictures.
Oh, okay. Visual proof.
Exactly. So their first big idea, their first solution, is to basically put that missing harmonic information back in using additive synthesis.
Additive synthesis, like building the sound back up from sine waves.
Essentially, yes. The key insight, and they show this in figure 2, is that there's this direct link, technically a bijection, between a WavLM frame, the pitch at that exact moment, and the full spectrum, including all the harmonics.
Right, so because they're linked, if you have the WavLM part, you can sort of work out what the original pitch and harmonics must have been for that little sound slice.
You got it. And in singing voice conversion, we already know the target pitch we're aiming for, right? We're shifting the source singer's pitch to match the target melody and maybe their vocal range.
Makes sense.
So the idea is, When looking for those newest neighbors, those WavLM candidates in the reference library, don't just look for overall similarity, also look for candidates whose original pitch was close to the target pitch we want right now.
Okay, so it's a two-stage filter, almost. Find generally similar sounds first, then refine by pitch proximity.
Exactly. They actually grab a slightly bigger set of neighbors. First, they call it K prime, bigger than the usual K. Then from that pool, they specifically rank them based on how close their original F0 was to the target F0 we need for the conversion at that moment.
Smart. And then what? They take the harmonics from those best pitch-matched candidates.
Yep. They extract the harmonic amplitudes, how loud each overtone was from those top-ranked candidates. Then they take the desired pitch sequence for the converted voice, combine it with the averaged harmonic amplitudes from those selected candidates, and they basically reconstruct a waveform that only contains those harmonics. They use this formula, sin cum sum 2 omma 0t. Basically, F0t is your target pitch over time, and ant is the average strength of the nth harmonic, all properly scaled up in time.
Got it. So it's like recreating the resonant signature of the voice using the target pitch and the harmonic info derived from the best matches. And then this synthesized harmonic part gets merged back in.
Yeah, right. It's not just replacing the original signal. As figure 1 shows, this newly synthesized harmonic waveform, UT, gets fed into the hi-fi Jan vocoder through some special downsampling convolutional layers. It's like injecting this extra layer of harmonic richness into the vocoder's generation process.
So it guides the final audio generation to include those details. That's clever. It's not just pasting it on top.
Exactly. It provides that crucial harmonic structure that WavLM alone might underrepresent, giving you a much fuller, more authentic singing sound.
Okay, that tackles the dullness, the lack of richness. What was the second big problem they mentioned?
Yes. Concatenation smoothness. This is a common issue with these frame-by-frame methods like kNN-VC.
Because you're just picking the best match at each tiny time step, right? Without necessarily considering if it flows well from the last picked segment.
Precisely. You pick based purely on local similarity, like cosine distance between the WavLM frames. But doing that can lead to these unnatural jumps or discontinuities, especially noticeable when the singer holds a note for a while, very common in singing.
Right. The paper mentions artifacts like slurring, or maybe a kind of trembling sound.
Yeah, exactly. That sort of thing. Figure 3 in the paper gives a good visual of this. You can see how it might pick segments that just don't line up smoothly over time.
And just picking more neighbors, increasing K, that doesn't really fix it.
No, not really. That often just brings in lower quality or less similar candidates, which can actually make the smoothness worse or introduce other problems. It dilutes the quality.
Okay, so they needed a more targeted solution for smoothness. What did they come up with? Looks like a couple of these working together again.
Yeah, a two-pronged attack, you could say. First, they changed how they measure the distance or similarity between frames, making it aware of time. Second, they changed how they combine the selected candidates.
Okay, tell me about the new distance metric.
So they introduced this new measure, L total. It's basically the original similarity score, LSRC, which is still important for local accuracy.
The cosine similarity.
Right. But they add a second term, L-concat, multiplied by a weighting factor M. And this L-concat term introduces a temporal cost.
Temporal cost, meaning?
It measures how similar the current candidate frame is to the candidates that were actually selected in the previous time step. It's looking backwards slightly.
I see. So it encourages picking candidates that are not only a good match for the current input frame, but also flow nicely from what was just chosen. It penalizes abrupt changes.
Exactly. It favors temporal coherence. And that M factor lets you tune the balun, how much you care about the immediate match versus the smoothness over time.
Makes sense. And is this computationally expensive, checking against the previous step?
They have a smart trick for that too. To keep things efficient, when they search for candidates for the current time step, they restrict the search. They primarily look at frames in the reference audio that immediately follow the candidates chosen in the previous step.
Like looking for continuation.
Precisely. It's an autoaggressive kind of reselection. Figure 4, the top part, illustrates this idea. It narrows down the search space significantly.
Okay, that's the selection part, biasing towards smoother choices. What about the second part, combining them? They don't just average them anymore.
Right. Simple averaging can still wash out details or fail to fully smooth things if some less than ideal candidates sneak through the selection process, so they use a weighted combination instead.
Weighted based on what?
Okay, this is pretty neat. They define concepts called ideal right continuation and ideal left continuation. Imagine you have your set of chosen candidates at time t. The ideal right continuation is basically what you'd get if you took those exact same candidate segments but looked one frame forward in the original reference audio.
Okay.
And the ideal left continuation for time plus 1 is what you'd get by looking one frame backward from the candidates chosen at time plus 1.
Right, so it's like projecting the chosen segments slightly forward and backward in time within their original context.
Exactly. And the goal of the weighting is to find weights for the candidates at times such that their weighted combination is as close as possible to the ideal left continuation coming from DIT plus 1. And simultaneously, the weighted combination at DIT plus 1 should be close to the ideal right continuation from DIN.
Whoa, okay. So it's trying to make the transition seamless by optimizing the weights to match these ideal forward-backward projections.
You got it. They set up an optimization problem to find the weights, W, that minimize the difference of the squared error between these combinations and their ideal continuations, with the usual constraints that weights have to add up to 1 and be non-negative. Figure 4, the bottom part, shows this weight optimization.
And the result of all this complex weighting
Is a much smoother output. By calculating these weights carefully, they can effectively downweight any remaining candidates that might cause temporal glitches, ensuring the final combined vector flows much more naturally. Figure 6 really highlights this. You can see how the optimized selection avoids those misaligned segments you saw earlier.
Okay, wow. So they've hit it from both sides. Inject the missing harmonic richness and enforce temporal smoothness during the concatenation. That sounds really comprehensive. Did the experiments back this up?
They did. They ran quite a few tests. Used LibreSpeech for speech-to-speech conversion just as a baseline, and then OpenSinger and NUS48D for singing voice conversion. NUS48 is interesting because it allowed for a cross-lingual test converting, say, Mandarin singing to an English singer's style.
Oh, that's a tough test.
Definitely ups the challenge.
Yeah.
And they used standard objective metrics WHERE and C for intelligibility, EE for speaker verification like similarity plus subjective tests.
The human listening tests, MOS and SIM.
Exactly. Mean opinion score for naturalness, how pleasant it sounds, and a similarity score for how much it actually sounds like the target singer.
And the results. What did Table I show?
Well, the big takeaway from Table I is that kNN-SVC, the full proposed method, consistently scored better on ER, MOS, and SIM compared to the baseline kNN-VC. And this was true for both speech and singing tasks.
Better similarity, sounds more natural. What about intelligibility? Did worse or suffer?
Very little trade-off there. The scores were pretty comparable, which is great. It means they got these quality improvements without really sacrificing clarity.
And it seems like both the additive synthesis and the smoothness optimization really contributed, looking at the ablation studies in that tape.
Absolutely. The full model with both components outperformed the versions with only one or the other. They really work together synergistically.
Any comparisons to other state-of-the-art methods?
Yeah, they compared against NUCO-SVC, another recent method. kNN-SVC's non-parametric additive synthesis seemed more robust, especially on that tricky cross-lingual task. They also mentioned models like Sovitz-SVC and DDSP-SVC.
Right, those are quite popular.
But pointed out they usually require speaker IDs, so it's not a perfect apples-to-apples zero-shot comparison. Still, the partial comparisons they included showed kNN-SVC holding its own, performing very competitively.
Okay, so summing it up, the big steps forward here are 1, getting those crucial harmonics back in via additive synthesis for a richer, more natural singing tone.
Yep.
And 2, these clever smoothness optimization techniques, the time-aware distance metric and the weighted combination, to make the stitched-together audio flow seamlessly without weird artifacts.
Nailed it.
Yeah.
It really feels like they've tackled some fundamental limitations of using these concatenative nearest neighbor approaches for the specific demands of singing.
And the impact seems pretty significant for the field, right? This opens doors for better zero-shot singing voice conversion without needing tons of data for every single speaker.
Definitely. You can imagine uses in music production, maybe tools for amateur singers, accessibility applications, even just more expressive synthesized voices for communication. Lots of potential.
And if folks listening want to hear it for themselves or even play with the code?
Yeah, the authors provided links in the paper. There's a project page, kNN-SVC.com, with demos, and the code is on GitHub user SmoothKen, repository kNN-SVC. Definitely worth checking out.
Cool. It's always great when you can actually hear the difference these techniques make.
For sure. The demos really sell it.
So, thinking beyond this paper as we wrap up, this focus on improving a non-parametric method, kNN-VC, with these targeted additions, It makes you wonder, doesn't it?
How so?
Well, could this general strategy, taking a powerful nearest neighbor approach built on large data sets and then intelligently refining specific aspects like harmonics or smoothness here, be a really strong path forward in other areas of generative AI, not just voice?
Interesting point. As an alternative to purely end-to-end parametric models.
Yeah. Like, what are the trade-offs? Maybe more interpretable results sometimes, better handling of rare cases captured in the large data set, but maybe less flexible in interpolation. It's definitely food for thought about where generative modeling might go next.
It is indeed a fascinating direction to keep an eye on.
Absolutely. Well, thanks for joining us for this deep dive.